everyone, welcome to the next session on virtual labs. In this session, we are discussing the fourth experiment of Machine Dynamics and Mechanical Vibrations Lab. The title of the experiment is Forced Vibration of Single Degree of Freedom System. The aim of this experiment is to observe the effect of damping in forced vibration of single degree of freedom system using a harmonic force. Forced vibration, as we know, is the application of an external force in the form of either a sine wave or a cos wave, or it could be an impact load or a step load. So we are going to give some kind of a load to the system and we are going to analyze how the body or the system is responding to an external force. Till now we have discussed about free vibration, which means there was some excitation to the system and on its own it was showing some kind of a reaction and then it used to come to a halt after a period of time. Here we are going to apply a force which is going to cause the system to vibrate and we will observe the response of the system. Also, we will be varying certain parameters and analyzing the system as we always do, because this is a simulation kind of experiment where you can vary your input and you can check the output. We are now in the theory section. Let's see what's given in the theory part. When an applied force causes the system to vibrate, it is considered as a case of forced vibration, and external excitation is often reduced to one of the following types. The first excitation that could be given is an external harmonic force. We are all aware of a simple harmonic force wherein a constant amount of force in the form of a sine wave or a cos wave is continuously given to the system. Let's read the equation given. Mx double dot plus Cx dot plus Kx is equal to F. In the previous analysis when we were talking about free vibration, this F was equal to 0. In the forced vibration analysis, this term is going to exist and it will have a particular magnitude, which means a particular value. Now this can be written in the form of an equation like it is shown here, F naught sine omega t. F naught is the magnitude of the force. Sine indicates the pattern of wave. So it will be a sine kind of a wave. T is the time and omega is the frequency with which you are applying the sine wave. Next comes the term of base excitation. Mx double dot plus Cx dot plus Kx is equal to F again, and this F can be in the form of this equation. So we are seeing the second type of excitation which can be given, that is base excitation. You have an equation here, Cy dot. C is the damping effect, Y is the velocity, K is the stiffness of the material and Y is going to be the displacement. This Y can be of the form Y naught sine omega t. It is the motion of the base. Again, this is a sine kind of input given to the displacement effect. Its velocity can be considered here, Y naught, and this total equation is nothing but the force, which is the base excitation given to the system. The third form of excitation, external excitation, which can be given is the rotating imbalance. So you can have an off-center rotating object which is causing some disturbance to the entire system. Now this is a very common example. Any object, for example a diesel engine, in that there could be certain rotating masses. Those rotating masses can cause imbalance to the system. So that is also a form of excitation to the system. So this equation mx double dot plus Cx dot plus Kx, which was equal to F, is now written in the form of m naught e omega square sine omega t, where m naught is the imbalance mass, E is the eccentricity of imbalance mass. Eccentricity means it is not at the center, it is acting somewhere away from the center. So there could be an eccentric mass in the body, and omega is the angular velocity, as we already know, in radians per second of rotation. Next, we'll talk about the solution of these kind of equations. The solution of the forced vibration system consists of a steady part and a transient part. Steady part means it comes to a halt soon. Transient means it comes to a halt over a period of time. The steady state response is independent of initial conditions. The transient part comes to zero with time, as I just told you, and is usually neglected. So we neglect that transient part because we are mainly focusing on studying steady state response of a system. It is something which we obtain very fast, and it is something which is not going to vary, and it is easier to study because it is more of a linear type. When you talk about transient analysis, it goes mainly into a non-linear zone because your parameters are going to depend on time. So over a period of time, you will find the amplitude slowly reducing. So that's the transient part. The steady state response is of the form. Displacement is a function of time. So this is your amplitude or displacement, as you can call it, is equal to x naught sine omega t plus phi. This is the solution of these kind of equations, where x naught is the amplitude. Phi is the phase of steady state vibration. So you obviously have a phase difference. That is, when you apply a force of a sine form, it will have a particular amplitude. But when you apply it to the system, the amplitude is going to be modified, and so is the phase. For f is equal to f naught sine omega t, external harmonic excitation, the steady state parameters are given by this x naught is given by this equation, x st upon root of 1 minus eta square the whole square plus 2 zeta eta the whole square. And phi, that is the phase angle, can be given as tan inverse of 2 zeta eta upon 1 minus eta square. Now this xst, this is f naught upon k. It is a deflection due to static force f naught, and k is the stiffness of the material. So x stands for the amplitude because of some static deflection or static displacement in the body. Now this omega upon omega n is indicated by eta. In certain books it is also indicated by r. It indicates the frequency ratio. This is showing the frequency of the body, omega upon omega n, that is the natural frequency of the body. So this is how you can find the solution, and numerically you can get the solution of a particular problem using this equation. So we will see how we are going to analyze by using virtual lab. We'll first go to the procedure. In the procedure you can read, set a value of stiffness and mass for the system. As you can see, this kind of a simulation window will be given, wherein we can change the value of stiffness of the spring. We can also change the mass of the system and the damping ratio, as you can see here. Set a small value of damping ratio less than 0.707. Notice the natural frequency of the system, that is the solution that you are going to obtain directly, shown below the graphs. So this kind of a graph is going to be obtained, and here you are going to get the value of omega n. You can set a value of operating frequency which will be marked in the graph. So you can also set the operating frequency of this system. So this is one parameter which you can change and get the solution. Click on the right arrow to load the graph of magnification factor. So you can see here, there will be a particular arrow. If we click on that, we are going to get this graph of magnification factor and phase angle. This is the phase angle here. And we are calculating both of them versus frequency ratio. That was omega upon omega n. And we are indicating in this experiment by using eta. So eta value is also found, and this is how you are going to get the graph. If you set a particular value of stiffness, mass and damping ratio. When you click on the left arrow, you come back to the display system. You can edit the damping ratio. You may set the value between 0.35 and 0.707. Click on the right arrow to load the graph of magnification factor and phase angle versus frequency ratio. So again, you can get another graph. You can see initially you got this blue graph. Now we are getting this kind of a graph. First the value of zeta was 0.07, which was very less. Now it is increased to 0.41. So you can see the magnification factor versus frequency ratio graph, and also you can see the phase angle, this green color, with a change in zeta. Now let's set the value higher than 0.707, that is 0.9 has been given, and let's see the solution. This red one is a solution now. You can see this is how your graph is obtained for magnification factor versus frequency ratio, and this red color now is the phase angle. So this is the procedure. Now next let's go for the self-evaluation tab. Here there are many questions given. You can just go through them, find out the answers, check if your answers are correct. Like suppose if this is given, this gives a steady state amplitude. If you look carefully, this one term is missing here. So that's why this answer is not correct, it's false. Solution of forced vibration consists of only the steady state part, or it is going to actually contain both. So we'll click on this. What is the governing equation of forced vibration with harmonic excitation? When you have harmonic excitation, that is the first one. This is the solution. This is also correct. Which of the following is the forced vibration system? Wind blowing at treetop, ocean waves at offshore rig, car moving on a rough road. I think all of these are the answer. That's the correct one. And last one is here. Under static condition, due to an operating force, if a 10 Newton per meter stiff 10 kg system undergoes a deflection of 10 centimeter, what is the amplitude of force? So you can calculate the value of force. When you know the value of K, you know M and the deflection. Look here. XST is F0 upon K. So I want to calculate F0. I can multiply XST into K. So 1 is the answer. That is correct. So we have solved all the answers. I'll click it once again for you. You can check 5 out of 5. So all are correct, which means these are the answers for this question. And that's how you're supposed to solve this. First go through the theory part and then solve here. Next we'll go for the simulation. As told in the procedure, we'll first change the stiffness value. Also we'll change the mass to a certain value. The damping ratio initially should be very less. It should be less than 0.3. So let me make it to 0.18. Let me keep the force amplitude to 10 Newton and forcing frequency as 6 radians per second. This is omega. So when you start, you can see this kind of a force applied. You can see this is of the sine form, as I was telling you. You can see here this is the omega n, natural frequency for this kind of a system. Eta and zeta. Zeta we have already taken, it is shown here. If you check on the graph, this is the kind of graph which is obtained. This is the graph of magnification factor versus the frequency ratio, and here this is the phase angle versus frequency ratio. Now I'll click on this arrow to go back to this tab. I'm not changing the stiffness and the mass. I will change the damping ratio as it was told between 0.3 and 0.7. So let me take it as 0.47. You can see the change here. If you want to calculate omega n, take the root of K by M. You will get the answer. I'll start the graph again. And then we'll go for the graph. This is for the second reading that we have taken. As in the lab, we always take 3 readings. Let's take the third one here by changing the damping ratio more than 0.7. So let's take it as 0.85. You can see here, zeta has got changed. Omega n is not changing because it is the ratio of K by M. We have not touched K by M in the second and the third reading. It's still the same. Hence, omega n is going to remain the same. We'll play the button. And now go for the graph. So this is the third graph that is obtained. So once you are done with this, you can again clear the graph and again go for another set of reading, a fresh set of reading. Apart from this, you have an assignment question given to you. You can just go through this and try solving it. There is another quiz given here. Try solving that, and the answers can be easily checked as I told you. This is the demo for how to conduct the simulation. These are some references given. And finally, you have the feedback section. After analyzing the entire experiment, if you have any suggestions to provide, you can go to this link and give some suggestion. So with this, I end the session. I hope you have understood how to analyze force vibration of single degree of freedom system. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.